Hi, I'm Tom Bell from ConcealFab, and what I'm going to do is give you a quick demonstration of the PIM Hunter testing process from Anritsu in combination with the PIM blankets available from ConcealFab, all for trying to solve the external passive intermodulation problem. So let's go over real quickly what the setup is. First off, I have a standard battery-operated PIM analyzer transmitting into an antenna, which is radiating objects out in front of the antenna. And what we're trying to do is identify where are the passive intermodulation problems in front of this antenna, as well as show that if we correct them, how much improvement in dBs can we get. So let's go back over here to begin with. I'm going to turn on the PIM analyzer. And right now I'm getting a PIM level from this system of neg 67, neg 68 dBm. That, and also it has the words IM overload, which means that whatever's causing the PIM in this system is so bad that it's saturating the receiver of the PIM analyzer. The other part of this system is the hunting system. So in the PIM Hunter, I've got a MS2720T spectrum analyzer set to burst detect mode with the IM3 signal that's being generated by my test tones. I've tuned the spectrum analyzer center frequency to match that IM3 frequency. And I've set my bandwidth or span to be 100 kilohertz around that signal. So I can see very clearly there's the CW signal at IM3 that is being generated by the test tones on the PIM analyzer. I come through an interference reduction filter that's designed to prevent those transmit signals from the PIM analyzer from coming back through the probe and hitting the front end of the spectrum analyzer. The spectrum analyzer front end could be one of the worst PIM sources on the cell site, so you want to make sure that we're preventing those high-powered tones from making it back into the spectrum analyzer. And then this connects to the PIM Hunter probe. The PIM Hunter probe is low PIM by design, so when I put it in front of the antenna system, it's not going to generate PIM. It's also designed so that it allows me to keep my body out of the way of the measurement. It also is designed to be isotropic, so that I turn and rotate the PIM probe just in normal business while walking around hunting for PIM. I don't want to see the orientation of the probe impacting the magnitude of the measurement. Now what we're going to do is we've set a limit line on the spectrum analyzer, which is about 10 dB lower than the magnitude of the PIM that we're hunting for. And I've turned the limit alarm on so that when I detect a signal that's larger than that limit line, the analyzer is going to make noise. So it's just like metal detecting at the beach. You want to be quiet when there's nothing of interest, and when I get on top of something that's interesting, I want to hear an audible sound so I can stop, pay more attention, and focus in on where is the problem. So now let's start doing our interference hunting. So I know I've got an antenna out here, I have all sorts of objects, I'm looking for the worst offenders at this point. And as I move the probe tip around, there's something of interest, but it doesn't seem to be the PIM problem I'm looking for. And then I come over here and start moving up here. I'm breaking the plane of that limit line. And you can tell by looking at this as I'm moving the probe tip that as I get closer and closer, the signal gets larger and larger at the maximum right next to it, and it very rapidly decays. And so I'm able to say the PIM problem here, I'm able to get this within probably about 3 inches. And when I come over to this other side and probe around, I don't find anything of interest until I come up over here and find the other PIM source. And once again, you're giving me a great indication of where the problems are. So knowing where the problem is means now we can do something to fix it. And so I've got 2 different technologies for fixing that I'm demonstrating here. But one of them is our PIM blanket material, which is it's actually a reflective technology for preventing, as an RF barrier, to block the energy between the transmit antenna and the PIM source. And the other is RF absorbing foam. This is available from Cumming Microwave as a material designed to block passive intermodulation. This is an absorptive technology. This is reflective technology. Both of them will do the job. It's just a matter of picking and choosing which one is the right one for your application. So let's first start with our PIM material, and I put it over and I cover one of the PIM sources. If I look now at the PIM analyzer, I see that it doesn't know it. It still says, hey, well, no, it actually did improve a little bit. We're down to negative 73. So I made a little bit of an improvement, but I haven't fixed it because I still have PEM problems on this site. Because we identified two, let's go ahead and take this tube here, which has RF absorbing foam in it, about a ½ inch in thickness. Let's put it over the opposite PEM source that we found. And now looking back at the PEM analyzer, we've made good progress. We're down to minus 91, minus 92. But if you look at the limit line, we're not done on this site until we get it to negative 97. So we still have more PEM to look for. I'm going to stop this, restart the test, give us a little more time. And now I'm now looking for a lower level PEM source. If I continue probing, I'm not going to find anything because I'm looking for something now that's lower than my limit line. So what I want to do is adjust my limit line. So let's go to Shift, Limit, Limit Move, and I want to move it by, let's say, 1 dB. I need to drop it down to a level that's appropriate for looking for a minus 90 dBm signal. So now my limit line's moved. Let's go to Shift, Trace, reset my trace, so I'm resetting that max hole, and now I'm going to start looking for where is the PEM problem that's giving me this negative 91 problem. And so what's interesting here is this is the problem, but even within this bag of steel wool, I can tell you which corner of the steel wool bag is the problem. But here clearly is something that's giving me an indication as being the next biggest PEM source I'm looking for. So let's go and use our PEM blanket as a way of suppressing that particular PEM source. I'll cover that PEM source. And now if we look over at our PEM analyzer, we are now below the pass fail level. But it's jumping. We're at negative 100. I saw a negative 98 there. I'm really a lot closer to the level than I really would like to be. So let's start over again. I now have this limit line that I'm going to move again. Shift, Limit, Limit Move. I want to move it by a dB at a time. Let's push it down, and let's say I'm looking for things that are popping up to be high enough to break a negative 100 type of an issue. Press Enter, and now let's go hunting again. So we'll go back over and say, did I fix the one with the PEM blanket? Yeah, looks like that's not the problem. Let's go look at that first PEM source. Yeah, it doesn't seem to be an issue. Let's go to the first one, or this next one. Oh, wait a minute. The one covered with the RF absorber is still giving me a strong signal. And that's because typically I need about 1 inch of RF absorber to truly be effective for finding these problems. So let's add more RF absorber in front of the second one. And now we'll go back and look at our PEM signal. You'll see now the PEM is down. Clearly, we picked up another 5 or 10 dB. So we're now down at a minus 112 dBm, or minus 1, well, you can't look at dBc on this because we're doing our testing with 2 watts to be safe. But clearly, we've driven the PEM down to a level that's significantly below the pass-fail level. By using the PEM probe and the PEM hunting system, we were able to precisely identify the problems without having to guess to figure out where the PEM was located.